Hi, this is Thirupathi. I am from Triple department. I am working as assistant professor in Marri Laxman Reddy Institute of Technology and Management. Today, I am going to deal power electronics. In this power electronics, we have a second unit, that is AC to DC converter. So this AC to DC converter is also called as rectifier. So here we have some topics in the unit 2, that is AC to DC converter. The first topic is phase control techniques, single phase controlled converter with RL load, single phase full controlled midpoint, single phase full controlled bridge connections with RL load and RLE loads, derivation of average load output, average load voltage and current expressions of load voltage and current, and some numerical problems after completion of these topics. And overall, three-phase converters and bridge connections with RL load, load voltage and current with R and RL loads. Effect of source inductance, dual converter waveforms, and some more numerical problems. So today we will discuss some basic circuits of rectifier AC to DC. So in that, the first one is single phase off wave controlled converter with RL load. So here you can observe the circuit diagram with a single thyristor T1 and the load R, and beside of that you can observe the waveforms of the load. So here the function of the circuit first we will discuss. So initially when we given a firing angle to the thyristor T1, then this circuit will be shorted. So when this circuit is shorted, the current will flow from source to the load, So at the thyristor VT1, the voltage is equal to 0, and at the load V0 is equal to Vs. So when the thyristor is on, the voltage across the thyristor is 0 and the voltage across the load is source voltage. Okay, and the current is also I0 is equal to Is. So from the waveforms we can observe here at alpha we given a firing angle. So when we given a firing angle, the thyristor is on. So the output waveform will start from the alpha to pi. So this is the maximum Vm. So here the device thyristor T1 will be operate for only single pulse. In the source pulse we can observe we have a negative pulse and a positive pulse. So positive pulse is 0 to pi and the negative pulse is pi to 2 pi. So a single device will be conduct for a single pulse. So here we are considering the thyristor will conduct for positive cycle from 0 to pi, and when we given the alpha, from the alpha it will conduct up to the pi. So if you observe here we taken some angle alpha. So from the alpha to pi the thyristor is conduct. After pi it have a negative pulse, so that negative pulse will be act as a reversed bias for the thyristor, so that the thyristor will be turn off. When the thyristor is turn off, the voltages will be, if you see here, the thyristor is turn off, the voltages will be at thyristor VT1, the voltage is source voltage Vs and output V0 is equal to 0. So in the waveforms, if you observe from the pi to 2 pi, the output voltage is 0. So after 2 pi is also we can observe it is 0, but till we give the triggering pulse, it will not conduct, so that the output voltage will shows as 0. So here from 0 to alpha we didn't given any triggering pulse, so output is 0. From alpha to pi we given a triggered pulse, so that the thyristor is in conduction. So we got the output voltage V0 is equal to Vs, and after pi, if the reverse, due to the reverse pulse, the thyristor will be in reversed bias, so it is turned off. So the output voltage is 0 up to 2 pi and next given triggered pulse. After 2 pi plus alpha, if we give the triggered pulse, then it starts conduction till again 3 pi to the triggered pulse. Okay, so if you observe below, here we have the current output. So in resistive load, the output of the voltage and output of the current both are looks like similar, but the amplitude of the current is less than the voltage. Okay, and here if you observe the voltage across the thyristor, so here already I told you from 0 to alpha we didn't given any triggered pulse, so the source voltage will be applied across the VT1. So we can observe here it is observed across the VT1, and at alpha we given a triggered pulse. So when we given a triggered pulse, so the voltage across the thyristor is 0. If you see here in the characteristics, alpha to pi, the VT1 equals to 0. From the pi, the negative pulse will becomes, so that at the voltage VT1 we will get the negative volt. So that negative voltage can be observed here. Okay, so this is the operation. So this can be, we can draw neatly. See here. So the stepwise we can draw neatly. So this is the taper transformer. So when we not given triggered pulse, then here if you see it is act as a open circuit. So VT1 is equal to Vs. So here the V0 is equal to 0 and I0 is equals to 0. So when this operation will be happens means when T1 is equal to off, so omega T equal to 0 to alpha, the V0 is equal to 0 and VT1 equal to Vs. So when we given a triggered pulse, then the circuit will become as we can observe here. So it is shorted. So here it is shorted. So when it is shorted, then VT1 equals to 0 and the output voltage V0 equals to, output voltage V0 is equal to Vs and I0 equal to Is. So the conduction period is when the T1 is on. So the omega T is equal to conducts from alpha to pi. Again we will give the triggered pulse, then it will start conduction. So this will be continuous as a cycle. So this is the function and this is the operation of the single phase half wave controlled converter with R load. So if you see here we have a derivation to find the average voltage, to find the RMS voltage. Okay, so here if you can see, to find the average voltage, here EDC is equal to 1 by 2 pi integral of alpha to pi. Here why we are considered alpha to pi means it will conduct from alpha to pi. So that conduction period limits we have to consider. So alpha to pi. So here Em sin omega t is the function. So if you do the integral, so we will get sin omega t integral is cos omega t. So by substituting of the limits alpha and the pi, so minus cos omega t. Here the cos omega t value we substitute with pi. So cos pi equal to minus 1. So already here we have a minus 1. So minus into minus it will get plus. So we got 1 here. After that here we have a minus. So minus minus plus. So we substitute the alpha. So overall we get the average voltage of the R load single phase half wave rectifier is Em by 2 pi into 1 plus cos alpha. So when we will get the maximum voltage means alpha is equal to 0 degrees. When alpha is equal to 0 degrees, we will get the maximum voltage. So substitute this alpha equal to 0 degrees in the cos alpha. So cos 0 is equal to 1. So 1 plus 1. So 2 will be cancelled. So here Em by pi. And here we have a average current ID is equal to Em by 2 pi r into 1 plus cos alpha. So by doing of this derivation, we can find the average voltage and the average output current. And here we are going to find the RMS load voltage is calculated. So in this RMS load calculates, here RMS equal to 1 by 2 pi integral of alpha to pi. So Em sin omega t whole square d omega t under root, it is under root is denoted as 1 by 2. So equals to, here Em square is taken out. So here we have a sin square omega t. So here sin square omega t can be written as in the formula of 1 minus cos 2 omega t by 2. So we know cos 2 omega t can be written as 1 minus 2 sin square omega t. So from this formula we can simplify it so that we will get sin square omega t is equal to 1 minus cos 2 omega t by 2. So this formula is substituted here. So after substituting here, we segregated 1 by 2 separately and cos 2 omega t by 2 separately, and substituted the limits of alpha and pi. After substitution of the alpha and pi, here we will get the equation ERMS equal to EM by 2 root pi into pi minus alpha plus 1 by 2 sin 2 alpha under root. Okay, so this is the ERMS. So to find the IRMS equal to ERMS by R, so EM by 2 r under root of pi into pi minus alpha plus 1 by 2 sin 2 alpha under root. And here the power PRMS equal to ERMS into IRMS. So we know ERMS value and IRMS value. By substituting it, we get the value. Okay. So this is the concept of single phase half wave controlled rectifier. This is the basic circuit which converts AC to DC. So next, just before we seen the load R load. Okay. Now we are going to see the load change with the R. We are changing the RL load. So if you see here, we have R and the L. So we know the basic of the inductor. So inductor is a device which will not allow sudden change of current. That is the property of the inductor. And the next one is the inductor can store the energy in the form of magnetic field. That stored energy can be utilized as supply. So here we can see, okay. So in the same manner, here also we have the circuits, you can see. So initially when the thyristor is not triggered, so at that position it is open circuit. At that circuit it is open circuit. So here R, L. So when it is open circuit, we know here VT1 is equal to Vs, and the output is equal to V0 is equal to 0. V0 is equal to 0. So here we can observe from 0 to alpha, the thyristor is turn off mode. So the output voltage and the output current is 0. So the total supply voltage will be across the thyristor VT1. So from the output, from the waveforms, we can observe from 0 to pi, the source voltage will be applied across the VT. Okay. So after alpha we triggered. So when we triggered, then we know it is shorted. So it is shorted. So when it is shorted, this VT1 equals to 0, and here the V0 is equal to Vs and I0 is equal to Is. Okay. So here it will conduct from alpha to pi. It will be in the conduction period. So here if you observe the alpha to pi, it is in the conduction period. So after pi, again the negative pulse will be present across the thyristor. So it is in reversed bias. Then the thyristor undergoes turn off. But due to the inductor, it will not turn off. So the polarities of the inductor will be changes. So that now the inductor will be act as a source. So this inductor will supply the energy to the thyristor. So this thyristor again starts conduction in the negative region from pi to here in the waveform we can observe T01 to T11. So this angle is beta. So beta is called as a extinction angle. Beta is called as a extinction angle. So till the inductor energy becomes 0, this beta extinction angle will be present across the waveform. Okay. So this T01 and T11 is the extinction angle beta. So after T11, the inductor energy becomes 0, and Along with that, the thyristor is in turn off condition, so the output voltage is 0. So from T1 to T2, the output voltage is 0. After again triggering at T02, again its conduction from T02 to again 3 pi. So this will be continuous. So if you observe here, the inductor current, the load current slowly increases to my maximum value at T01. Why? Because we know the inductor will not allow the sudden change of the current, so that it is slowly increases. So slowly it starts going to be decrease. Okay, so after the T11, the pi plus beta, at the point of pi plus beta, the output current is 0. The output current is 0. So here we get a 0. Again, when we triggered, again it slowly increases. Again it will become 0. So it's go on do the function like a cycle. Okay. So this is about the RL load. So now in the single phase half wave controlled converter, we see with the R load and with RL load. Okay. So here the main points is that when the thyristor is on, then the voltage across the thyristor is 0, and across the output is total voltage of source voltage. If the thyristor is off, the voltage across the terminals is maximum, okay, and the output voltage is 0. But the current in the R load is same as the output voltage, but in the current in the RL load, it is not same as the output voltage. Why? Because due to the inductor property, it will not allow the sudden change of the current, so that it slowly increases and slowly it's become 0. Okay. So this is the operation of single phase half wave controlled with RL load. So if you see here also we have same like a derivation. We will see here also. So here also we have a output voltage, output current, VRMS and the IRMS. Okay. So now, so we see output voltage V0 equals to 1 by 2 pi integral of alpha to beta. So previously we considered alpha to pi. So it is conducted up to alpha to pi, so that we taken as pi. But in RL load, after pi, the inductor is acting as a source. So due to that, some angle is extended. That angle is beta. So till the beta, it is in conduction period. So we have to consider alpha to beta. So here we know the equation Vm sin omega t d omega t. Vm sin omega t d omega t. So we know that 1 by 2 pi. So here if you take an integral, so it will become minus cos omega t alpha beta. So substitute the limits, so that it will come minus cos beta. So minus into minus cos alpha. So the equation V0 equals to Vm by 2 pi, here minus cos beta plus cos alpha. So the overall equation Vm by 2 pi cos alpha minus cos beta. So this is the average output voltage of the RL load. Average output voltage of the RL load. Okay. So to find so this is the output voltage. So if you see here also we have average load current I0 equal to Vm by 2 pi r cos alpha minus cos beta, and RMS load voltage we know VRMS is equal to 1 by 2 pi alpha to beta Vm square sin square omega t d omega t whole to the power of 1 by 2. Okay. So from deriving this, we got the RMS load voltage Vm by 2 pi r is equal to beta minus alpha minus 1 by 2 sin 2 beta minus sin 2 alpha whole root of 1 by 2. Okay. So these are the output average voltage, output average current, output RMS voltage. Okay. So we now studied about the load of R load and the RL load. So here actually here the one more important point is the thyristor is a switch. So when we switch off, the switch should be goes turn off. but due to the inductor, it's still in conduction. Okay, so to avoid that, here we are using the freewheeling diode. So if you see here, we have a circuit. Here we diode is connected across the load. Okay, so the same operation is for RL load. Here also the same thing. But the point is, when the thyristor is off, then this inductor is acting as a source. Now these freewheeling diode act as a forward bias. So when it is in forward bias, the current will be circulates from RL to the freewheeling diode. So that here, if you observe the output voltage at pi, it will become 0. After pi, it is also maintained 0. But in previously, after pi, we got some extinction angle, that is beta. But now it is not there. Why? Because due to the freewheeling diode. But in the load, it maintained a continuous current. But the load maintains continuous current. Why? Because due to the freewheeling diode, the current is circulated from the diode R and the L. So the current is not become 0. The current is continuous. Okay. So this is these freewheeling, by using of the freewheeling diode, we can turn off the device at pi and we can maintain the load current continuous. Okay. So today we discussed about today we discussed about the single phase half wave control rectifier with R load and the RL load and with the freewheeling diode. And we seen the derivations of output voltage, output current, RMS voltage of R load, RL load. Okay. So today here we are going to end this here. So thank you very much.